Did you know that the sun is 1.99 times 10 to the 30 kilograms?
No, I did not.
That's 199,000,000 followed by 28 zeros.
Dang, that seems pretty heavy.
That's unbelievably heavy because in pictures, the sun, it looks bigger, but maybe not crazy bigger than the Earth. But in reality, it's 330,000 times heavier.
That's a big number.
For comparison, if the mass of the Earth was the mass of a pencil, proportionally, the mass of the sun would be a truck.
Trucks are way heavier than pencils.
And speaking of trucks, check this out. Because the sun is radiating so much energy, it is losing mass based off E is equal to mc squared. And we're not talking small amounts of mass like pencils or grams. We're talking truckloads.
Truckloads?
So how much mass do you think the sun loses? Like one truck, two truck, 100 trucks?
Let's go 100 trucks. 100 trucks in a day.
Nope. The sun actually loses over 2 million trucks worth of mass every second.
Every second? Well, dude, we're gonna run out of sun. Like in 100 years, there's gonna be no sun left?
Well, let's see if that's valid. Let's consider 2 million trucks, and let's say each truck is about 2,000 kilograms. That's happening every single second. So let's times that by 60 seconds, then times that by 60 minutes, then times that by 24 an hour at how much is lost in a day. Let's times that by 365.25 days. That gets us how much mass is lost in a year. Times by 100 years, and we get 12.6 billion kilograms of mass will be lost from the sun in 100 years.
Well, then how much is gonna be left?
Well, let's take that 12 billion kilograms that are lost in 100 years, divide by the mass of the sun, and just times by 100% to figure out the percent that we lost. And in 100 years, we're going to lose 0.000000006% of the sun's mass.
Oh.
That's how freaking huge the sun is. And now you may be thinking, well, how do we know that? I mean, you can't really just take the sun, put it on a scale, and measure how much it weighs. You're right, we definitely can't do that. And how we determine the mass of stars and other celestial bodies is actually by looking what's orbiting around them. If we take how far they're orbiting and how long it takes, turns out we can figure out the mass of that star. And that's what we're going to do in this video. We're going to try and determine the mass of stars by looking at things orbiting around them. So let's take a look at calculating the mass of stars. All right, let's take a look at some equations for how we can calculate these unbelievably massive things based off of something going around in an orbit. And we're going to start with the orbit because it's going around in a circle. So going in a circle requires a centripetal force, Fc. And from previous lessons back here, we said Fc has to be provided by something else. In this case, it's being provided by that gravitational pull, always pulling it towards the center of the circle. So if Fc is equal to Fg, let's throw in our formulas for those two. Fc is mv squared over r. We covered that in a previous lesson here. And Fg is g m1 m2 over r squared. We covered that in quite a while previous in that lesson here. Now there's a lot going on over here. Let's see if we can simplify anything. I see a lot of m's. I'm going to put some colors up there to show that this is the blue mass going in orbit, and that kind of orange one is representing the star or the sun. So since we have the same blue mass on both sides, I can cancel out that mass. Going to make it a little bit easier. We also notice that there's an r on both sides. The r for the centripetal force is the distance from the edge of the circle to the center, so we can see it up there. And then the r for gravity is also the distance from the center of one mass to the center of the other mass. So that r ends up being the same as well. There's an r squared on the gravity side, so that's kind of like r times r. I can cancel one of those with the r on the Fc side. Okay, so this is looking pretty good. I got v squared is equal to gm over r. But how to figure out the velocity, how fast it's orbiting around? Well, I'd have to look at v is equal to d over t. So maybe we can sub some of that in. V is equal to d over t, the distance it travels in a certain amount of time. The distance that it's going to cover there, one lap around an orbit, is the circumference of the circle. And that's calculated with 2 pi r. That's the circumference of the circle, the distance it travels in one orbit. So I want to sub that number in for that, but that's velocity squared over there. So let's square all this number, square the v and square the entire other side. That's going to make it 2 squared, pi squared, r squared. We're just going to square everything on that side. Now that we have v squared is equal to this, I can sub that in over there for my v squared. And still looks a bit messy, but we're getting close. I can do a little bit more simplifying. I see some r squared on that side and r over here. Let's group our r's together by bringing those to this side. Now I have r squared times r, so that'd be r cubed. To get the mass by itself, I'm just going to switch it out with the t squared. And this gives us a formula that's on most data sheets labeled as orbital period. Time or period squared over radius cubed gives you 4 pi squared over gm. We also looked at this earlier in Kepler's laws and found that this gives us a constant number, or Kepler's constant. You can find that video up here as well. But in this video, we're trying to solve for the mass of that star up above. So let's rearrange it for mass, and we get this formula to calculate the mass of the star. Let's say we have 4 pi squared. That's just a constant number. The radius, how far it is from the star, we can measure that. Divided by t, the time to go around, squared, we can measure that. And g is a constant. So this enables us to figure out the mass of a star simply based off how far it is away and how long it takes to orbit. These equations are quite big and scary, and the far one there is on the formula sheet, and I refer to this to my students as the big scary equation because there's a lot going on in it. But let's take a little bit closer look at this big scary equation. Yeah, okay, there's our big scary equation. All right, it looks intimidating. There's lots going on. There's squares, there's cubes, but I'm going to show you how if we treat it properly, we can turn this big scary equation into not too bad of a monster over here. So how are we going to turn this into a more friendly looking equation? First thing is you need to make sure that t, your time, is always in seconds. That's because this capital G is a constant number based off of meters, kilograms, and seconds. So we need to have our time in seconds here. Another thing to remember is that the radius always has to be from the center to the center. We've had that pretty much throughout this whole chapter, but it's a good reminder that we have to remember to do that. If it ever mentions height above the surface, make sure you add the thickness of that planet or star, whatever you're being asked about. And last one, although he looks kind of friendly right now, only use him when it's absolutely necessary. Because it's the biggest equation, it's the most likely that you'll make mistakes. Try and use the other ones first. The other ones that we use in this chapter were orbital velocity. There's a link to that video up here. If it ever mentions an orbital velocity or asks for velocity, go to that equation. But if it hasn't asked for velocity, hasn't given it, we're not going to use that one. Before I used the scary equation, there was one other option that we could use, which was Kepler's. If you have two things orbiting the same thing, we can use just this ratio to compare their time and radius. But if I don't know of two things going around, I only know one, I can't use that equation either. So if it doesn't mention velocity, I don't know two things going around, that's the time when it's absolutely necessary to use the big scary equation. So let's try an example here. It says a new star is discovered if it has a planet that orbits at a radius of 2.15 times 10 to the 11 meters once every 400 days. What is the mass of this star? Okay, so we have this problem with the information above, and you might be thinking, okay, I'm going to use the big scary equation, but remember, don't use it
until it was absolutely necessary.
So let's check that. Does it mention anything about velocity? Can I use my orbital velocity equation because that's easier? No, it doesn't ask me for velocity. It doesn't give me a velocity. I can't use that one. Well, do I know of anything else going around this star? I could use the comparison here to try and figure that out. No, I don't know of anything else going around it. I can't use that equation.
Looks like it's absolutely necessary.
I think you're right. It's time to use the big scary equation. But if we treat it properly, it won't be too bad. Okay, let's get that equation up to the top. Remember, we are solving for mass. You might have been thinking when I put up Kepler's law there before, he said there isn't mass involved there. That's true. This equation is sometimes used to solve for period, radius, or mass, so there's some variety of different questions you can get where you have to narrow it down to using this equation. But we've done that here. We've narrowed it down to we need this equation, and this is asking us for mass. So we got to rearrange for mass. It's in the denominator there. I'm going to swing that up to the top, swing everything else to the other side, just like we did earlier in the video, and we got this rearrangement for mass, 4 pi squared over r cubed, divided by t squared and g. Let's plug in our numbers here. There's a lot to put in. First, I have 4 pi squared. Fortunately, that's all a constant. Let's put that in our calculator and use the pi button. Don't just enter 3.14. Use the pi button. That'll use it to more significant digits. Next, we're going to put in our radius, 2.15 times 10 to the 11. It told us that's the orbital radius, so that does mean center to center. Again, if it ever mentions anything above the surface of the planet or the surface of the star, add the thickness of that star. But orbital radius is already center to center. Make sure to cube that number. Don't forget this cube that's going out to the exponent of 3. At this point, I would hit enter. So let's go on our calculator, 4 pi squared times 2.15 times 10 to the 11. I'm going to put that in brackets, cube it, hit answer, and this is where we're at so far. Next, looking at the denominator, we have 400 squared times our gravitational constant, but that 400 is actually incorrect because that 400 is in days. Remember, we have to treat the big scary equation properly. We need our time to be in seconds. So how we're going to turn that into seconds, we're going to take it times by 24 hours, times by 60 minutes, times by 60 to get us into seconds. So let's put that all in our calculator here. It's quite a bit. We're going to go divided by, in brackets here, the 400 times 24 times 60 times 60. That's in brackets squared, that entire number. That's going to be our time in seconds squared. Then multiply that by 6.67 times 10 to the negative 11. Make sure that's all in the denominator. There's double brackets around there. I know that's kind of tough to put in. If you want to get the number for the denominator separate, write it down or write it in afterwards. That totally works as well. But I'm going to put it in with all these brackets and we get our final answer of 4.92 times 10 to the 30 kilograms. Pretty similar actually to our sun. A little bit bigger than our sun, actually. Actually about 2.5 times bigger. That's significantly bigger. That's a really big star right there. An unfathomable amount of mass, but now we know how to calculate that using this equation. And that's all we have for today's video. So thank you so much for watching. I hope you found that helpful in calculating the mass of stars and using that big scary equation. If you're looking for more helpful tips, I do have an entire course playlist of science courses at the channel here and the latest video from the channel over here. So again, thank you so much for watching and I will see you in the next video.